In this lecture, we're going to learn how to determine the moment of a force about an axis. In other words, we're looking for the projection of a moment in a given direction. To explain why do we need to know the moment about an axis, let's take a look at one example. Saying when we try to loose the nut on the tire, so this nut is located at this point O on the tire, we're going to loose it with a wrench. And the force applied on the wrench is pointing in the z direction. Now, based on the definition of moment, the moment equals to r cross f, where r is a position vector from the point O to any point on the line of action of this force F. So now this is the position vector r. And using the right-hand rule, the moment MO, which is the tendency of for the wrench and nut to rotate about point O, is located in this direction. Is actually within the x and y plane and point out like this. So, however, does all of this moment MO act to turn the nut? Actually, if you take a closer look or do an imaginary experiment, we know that the nut can only rotate about the y-axis. Therefore, to determine the turning effect, only the y component of this moment MO is needed. So that's why sometimes we do need to find the component of the moment along the given axis. It can be the x-axis or y-axis or any arbitrary axis. To determine the moment about an axis actually is to determine the projection of the moment onto that given axis. So let's review how to determine the projection of a vector. So if we have a vector A, and we have the direction AA, and then we can determine the components of this vector A parallel and perpendicular to the line using the dot product. So it is especially important for us to know how to find the projection of the vector on this AA direction or the components of the vector that is parallel to this given line. So we can use the dot product. The vector A dot the unit vector UA, whereas the unit vector UA indicates the direction of this line AA. And this dot product will give us the magnitude of the projection of vector A along the given axis AA. And sometimes if you need to find a component vector A sub A, we need to attach the direction of this vector. So again, using the dot product, we only have the magnitude of this projection. And the direction of the projection is just the same direction as this line A. So magnitude times unit vector, which will give us the component vector in vector form. Let's check the general steps to find the moment of a force about an axis. So the main difference between this lecture and the last lecture is, last lecture we are calculating the moment of force about a point O, for example, or point B. Today, we're looking for the moment about an axis, x-axis, y-axis, or z-axis, for example, or in a more general case, AA-axis in this example. So basically, there will be two major steps. The first one is to find the moment about a point, still be the moment about the point. And then we're going to find the component of this moment, or the projection of this moment along the AA direction. So that will be the moment about the axis. So here in this example, we have a rigid body or we have an object with arbitrary shape. So assume this is a 3D shape, okay? And we have the force F applied at point A on this body. And we're looking for the moment of this force. Well, think about you have a balloon. Well, not a balloon. You have a bottle. It's kind of squeeze the bottle with irregular shape, and then you're gonna pull on this bottle from this point A located on the bottle, and then this bottle is fixed on the stick. So this stick is AA. So that means you're gonna rotate, right? You rotate this bottle, plastic bottle. Now we're looking for the rotational effect of this force F on this bottle. So this bottle can only turn about this AA axis. So that's why we need to find the moment of F about this A axis. All right. So now this AA axis is denoted by this direction UA hat. So UA hat is the unit vector along the AA direction. So that's the direction of the AA axis. And now the first step to find the moment about the axis is we need to compute the moment of the force F about any arbitrary point O that lies on the A axis using the cross product. So the first step is to find the moment of the force about a point. Use the knowledge we learned from last class. And this point is an arbitrary point, but with a condition. It's any point on this A axis. So we call this arbitrary point O. So then we can find the moment of force about this point O, MO, using the cross product. So the MO is the tendency of the force to rotate the bottle about point O, or the axis actually passing through the point O, pointing in the direction of MO. Again, this will be defined by the right-hand rule. That means this MO has a tendency for the bottle to rotate about the MO direction, this direction. But we're looking for the component, right, along the A axis. So the second step is to find the component of this vector MO along the A axis, or to find the projection of the moment MO about a given line axis. So we just reviewed it. To find the projection of a vector on a given direction, we use the dot product. So MO dot the unit vector of the direction, or unit vector UA dot MO, both will give us the magnitude of the moment about the A axis. Similarly, if we need to find the moment vector along the A axis, we use the magnitude times the direction. Again, the direction is just UA, the unit vector along the A direction. This will give us the moment of the force F about the A axis. In conclusion, the moment of a force F about a given axis A can be obtained using triple scalar product, which means we can use the unit vector UA, which is the unit vector along the A direction, dot the cross product of R cross F, where R is a position vector from any point O on the A axis to any point A on the line of action of the force. In other words, this is our first step of the calculation. We look for the moment about a point O for the force F, where the point O is located on the line of action or on this A axis. After we find the moment about a point, we use dot product to find the projection of this moment onto the given A axis. And the result will be a scalar number will be the magnitude of the moment along the a-axis. So the triple scalar product method will work. Well, it's like we combine the 3 steps we just went through from last slides, combine them into one step. But my suggestion is still use the 3 steps instead of doing this triple scalar product. But if you want to try the triple scalar product, this is to replace the ijk hat term in the 2 by 2 determinant by the components of this unit vector, uax, uay, and uaz, and then perform the cross product as you do before. But again, this is just one optional method. My suggestion is still to take the steps. The first step is to perform the cross product to find the moment about a point O, which is on the a-axis, and second step is to perform the dot product to find the projection. So UA dot MO. So we do the cross product and dot product separately to prevent any error, and your solution will be better organized in this way. Let's check our understandings before we move into example problems. First, when determining the moment of a force about a specified axis, the axis must be along. So here you can pause the video and make your own choice. Maybe check your answer in 1 minute. Okay, so the axis can be any line in 3D space. So the idea here is for vectors, it's similar to a scalar number. For example, if you have a number 10, you can resolve this number into 5 plus 5, 2 components. Each components they have the same value, or it can be 1 plus 1 plus 8. You can resolve it into 3 components, and you can resolve it into even more components, or you can resolve it into decimal numbers. There are unlimited ways to resolve one number into components and still have the same value. Same idea for vectors. We can resolve vectors into any directions, and the result will be the same. So the basic idea is if you have a vector v here, you can resolve it in any number of components along any directions, as long as based on the triangular rule and the parallelogram, as long as the components, when you put the components in head to tail manner, as long as they will make a closed shape. So if I call this V1, V2, V3, V4, and V5, and I can say this vector V can be resolved into V1 plus V2 plus V3 plus V4 plus V5. And each vector component points to an arbitrary axis, and based on trigonometry or other method, we can find the direction and component and the magnitude of the components. Number 2, the triple scalar product results in, well, the cross product will give us a vector, and U hat is a vector dot product, right? The last step will be a dot product. Dot product is also called scalar product. So the triple scalar product, actually, the question already gave us the answer, right? So it should be a scalar quantity. And a scalar quantity, keep in mind, can be positive or negative. In this example, a force is given which has the magnitude of 200 Newton, and we have those direction angles given 60, 45, and 120. So with those angles, with the magnitude, this force is fixed or is defined. And we're looking for the magnitude of the moment of this force about the x-axis. So based on the steps we explained earlier, so here are the approaches we're going to take. So to find the moment about an axis, we're going to use the triple scalar product, or we're going to use the unit vector of the axis dot the moment of the force about a point. So that means first we need to find the force F in Cartesian vector form in order to perform this cross product. And we also need to find the position vector from the point O to any point on the line of action of the force, but currently we only know this point A. So this R, we're going to choose ROA, which means we need to find the moment about a point on the line of axis. So this point is the origin now, since this point O is in the intersection of x, y, and z axis, so it's the point on the x-axis. So we find the moment about this point, then we use the dot product. The unit vector of x-axis is I hat in this case. So I hat dot the cross product, or dot m of O. This will give us the moment of this force about the x-axis. Okay, so we're given with this diagram and with given information, we're looking for the moment of the force about the x-axis. So you can put the approach or the major equation on the top to remind you what the steps we need to take. So m of x overall should be equal to the u hat of x, which is actually I hat, unit vector along x direction, dot cross product of r, which will be RAO, cross the force F. Okay, so this is the formula we're going to use. So step 1, we said we're going to find force F in vector form. So we're given the magnitude of F and we're given the direction angles. Let's put down the direction angles of this force F. So the alpha is 60 degree. Oh no, sorry. Alpha is 120. So alpha is the angle between the x-axis and the positive x-axis and the head of the force F. And beta angle is the angle between the head of F and the positive y-axis, so beta is 60, and gamma is 45. So F can be expressed in component format immediately. The magnitude is 200 Newton, and the unit vector of the force equals to cosine alpha I hat plus cosine beta j hat plus cosine gamma k hat. Magnitude times unit vector will give you the vector of this force F. So we put those angles in: alpha 120, beta 60, gamma 45. And this will be solved to be negative 100 I hat plus 100 j hat plus 141.4 k hat in the unit of Newton. So this is the force in vector form. Step 2. Find position vector. ROA. R is any point on the line on the axis O is any point on the axis, and A is any point on the line of axis of this force. And based on the geometry given here, we can find this OA immediately. Actually, it will just be the coordinates of point A, since O has coordinates 0, 0, 0, and A has point 3 in the x direction, in the y direction, and then 0.25 in the z direction. So we can write our OA directly as well, which is 0 I hat, doesn't have any x component, 0.3 j hat, and 0.25 k hat. And unit will be meter. So step 3 will be find the moment about point O, which will be MO in vector form. It's ROA cross the force vector F. So I skipped the steps for the calculation. You should know how to perform cross product by now. And this is the result for the moment about point O. So this moment has 3 components. The x component, that's the tendency of rotation about the x-axis. And this is the tendency of rotation about the y-axis. So it actually will rotate about the negative y-axis. Magnitude is 25, and the tendency to rotate about the z-axis. So the last step will be we're going to find the x component by performing the dot product. And step 4 is to find the component of this MO about the x-axis. So we can perform the dot product and u of x dot MO. So u of x is just I hat, and dot, the moment we just calculated. And a quick reminder for the dot product, I hat dot I hat equals to 1. So the unit vector dot itself, the result will be 1. And the unit vector dot another unit vector, the result is 0. So because of that, our final answer will be 17.4. And I forgot the unit here. The unit is Newton meter, since the force we have the unit of Newton, and the distance or length has unit of meter. Therefore, the m of x has the unit of Newton meter. And this is our final result. Okay, so let's take a look at all of these steps. We are looking for the moment of the force about an axis, x-axis. So first, we need to find the force F in vector form in order to perform the cross product. And then we find the position vector, our AO, and this position vector is from any point on the line or on the axis to any point on the line of action of the force. Then we can perform the cross product to find the moment about this point O, which is located on the axis. And step 4 is to find the component of this moment about the x-axis. So let's take a closer look at the last step. Find the component of a vector about the x-axis. In other words, we're looking for the x component. And what is the x component? If you take a look at this vector MO, well, don't think about what this vector is for. It's just a general vector. Let's say this is just a vector, not a moment, not a force, it's just a vector. And if we have a vector, we call this is the x component, right? And this is the y component, and this is the z component. Now go back to step 4. If I ask you to find the x component of this moment, what is the value of the x component? 17.4, isn't it? And it's actually the same answer as we're performing the dot product. So now we realized the x component is just the x component of this vector m, or the tendency for this force to rotating about, or for this wrench to rotate about x-axis is 17.4, and if it's going to rotate about the y-axis, the component is 25, and the tendency to rotate about z-axis is 30. So in other words, step 4 can be omitted in the future if we are looking for the x component or y component or z component, or if you're looking for the component of this moment about the x-axis, then it will just be the x component. If we're looking for the y-axis, then it will just be the y component, and so far so on. So you don't have to perform the last step, the dot product step. So this step can be omitted. But if we're given an arbitrary direction, just like the example, the AA axis is not x or y or z, then the dot product is necessary. Let's take a look at the second example. And second example is very similar to the one we just did. We have a force with a magnitude of 30 Newton given, and also the direction angles are given, alpha, beta, and gamma. Also, the x, y, and z coordinates are set up at this point where the force is applied. And we're looking for the moment of F about this AA axis. So it's a question of a moment about an axis. So the approach here is, again, we need to find the moment about a point first, and then find the projection of the moment on this AA axis. So first, we need to find the unit vector of the axis, UA, based on given information. But here it's obvious that AA is parallel to the y-axis. If we take a closer look, AA is parallel to the y-axis. Therefore, we say this AA axis is actually in the y direction, or we say the unit vector is just a j hat. So again, the unit vector indicates a direction, and the vector can move parallelly in space as long as you do not change the orientation. All the parallel directions are actually indicating the same direction. So in this case, AA and Y, they are actually the same direction. So that will make things much easier. So we'll say just find the force in Cartesian vector form. Then we are going to find the moment of the force about point O. So this is the point O, a point located in the middle of this AA axis. So why we choose this point? It's kind of by experience, because you can choose any point on the AA axis, but you may not be able to figure out the coordinates of that point. So this point O is kind of located on the center line of this assembly, and you can find the coordinates of this point. on the AA line. So that's why we choose this point O on EA. So to find the moment of the force about the point O. And again, I think we're going to skip this step. So we're not going to use the dot product, since we know this AA direction is just the Y direction. So we just need to find the Y component of this MO. Then that will be the moment about this AA axis. So let's write down the steps. First, we're going to express the force in vector form. And this F will be the magnitude of the force times unit vector. Unit vector will be cosine alpha I hat plus cosine beta j hat plus cosine gamma k hat. And the values are given. Alpha is 60 degree, and beta 60, and gamma 45. And the force will be 15 I hat plus 15 j hat plus 21.21 k hat. The unit will be Newton. And second step is to find the position vector ROA directed from any point on the a-axis to any point on the force F. So it will be ROA. And we can write down the ROA in vector form. So from point O to point A, we can take the imaginary path, along the X and Y and Z direction. So first we can travel along the Z direction, so going up. So here I already did some, draw a line that is parallel to Z on my diagram to help me figure out the directions. So 3D diagram is a little bit hard to interpret, so you need to do a lot of practice to get yourself familiar with the procedures to find the geometry especially. Okay, so this will be my OA of Z, because that's along the Z direction. And then we need to make a turn, take a turn to travel along the other direction, which is now the X direction, but it's the negative X direction. And this will be the OA of X, and is a negative value. And it's doesn't have a Y component because it is within the XZ plane. Then we can find the values using geometry. So OAX is the length of this part, which is 100 millimeter. So we'll do 0.1 meter. And remember, is a negative 0.1 I hat. And same idea for the OAZ, we need to add the two vertical parts together. One is this length, 100 millimeter, and another one is this part, which is 50 millimeter. So we'll have 0.1 plus 0.05 j hat to express all the values in the unit of meter. So I have negative 0.1 I hat plus 0.15 k hat. Sorry, that's the k direction. So it should be, or z direction. So it has a k hat component, it doesn't have the y component. So this will be my ROA with unit meter. Step 3 is going to find the moment about point O using the cross product of RAO cross the force vector F. So the I hat term can be calculated by using 0 times 21.21 minus 15 times 0.15. So the answer will be 2.25. That's the I hat term. And after performing the cross product, we find the moment of about point O expressed in the vector form. And the unit here will be Newton meter. So if you noticed earlier, I converted all of the millimeters to meter already in the ROA step. So the last step would be, since we're looking for the moment about AA, and since we can say because AA is parallel with y-axis, so because AA is parallel with y-axis, so this moment in the AA direction actually is a moment about the y-axis. So it will be simply the y component of this MO we just calculated. So it's 4.37 Newton meter. And that is my final result.